Hello? Hello? Yeah. Hello. Okay, that's good.
Nice. Okay, wait, let me try jumping. Okay.
Hello.
Okay.
It's recording and sharing screen. Okay. Thanks for waiting, everyone. So my plan is to go through the 24 term 1 paper. I know you guys have the solution, so I'm not going to spend time going through every single detail of every question. Just want to teach you through the main concepts and use the questions sort of to help explaining those. Hopefully I'll finish this paper, before the 2 hours time, so that you can ask any questions about any other questions from any other papers if you want. So let's start with question 1. So question 1 is about power factor stuff. So we've got the circuit. And part 1 is asking us to find the average power, reactive power, and apparent power, as well as complex power for the source. This is a pretty straightforward question. Essentially, all you have to do is simplify the circuit and then calculate the power. Essentially, having the voltage source connected to one impedance. So I'm just going to transform this circuit to a voltage source with an equivalent impedance. Once that is done, I know the voltage across that impedance, and I can work out the current, and then we calculate complex power by doing V times I conjugate. Now, this formula holds when both of them are in RMS. If it's not given in RMS, then you'll have to add a half. So that's also equal to a half times V times I conjugate when it's peak value. Okay. So in this case, Z equivalent is simply just, so if you look at the circuit, it is these two in series in parallel with these two, and then that's in series. So that's going to be 60 plus J20 in parallel with how do I hide this? Okay, cool. So 60 plus J20 in parallel with 30 minus J10 and plus 20. And then whatever that gives us, we are just going to do I equals V over Z equivalent. And that should give us 5.71 with an angle of 3.33 degrees amps. And this is in RMS because V is in RMS. So this V here is the 240 volts. Right. Now that we've calculated current, we can just do S equals the RMS, IRMS conjugate. What conjugate does is it's just going to flip the sign of this angle over here. So you put that into the calculator and we get so 1371 with a phase of minus 3.33 degrees. Now this is the apparent power, so that's the magnitude of S. And this here is our theta. Another form of writing S is P plus JQ, so just in Cartesian form. And if we convert that magnitude phase to Cartesian form, we get 1368 minus J 79.6. And the units for S is volt amperes. So now the real part is the power, and the imaginary part is the reactive power. So we've got average power and reactive power, which is everything the question is asking for. Next part is asking us to sketch the power triangle. That's quite straightforward. The real part is P, the reactive power is Q, and the apparent power is the hypotenuse of the triangle, and that's our theta. The reason I drew the triangle downwards is because we can see that theta is negative. So a negative theta means we have a leading load, which usually implies capacitor. So the circuit we can say is net capacitive. So I'll just summarize the stuff here. So theta is equal to theta V minus theta I. And then we've got two cases. So either it's greater than 0 or less than 0. If it's greater than 0, then that's lagging and inductive, which means you draw the power triangle facing up. And if it's less than 0, then it's leading and it's capacitive. So in this case, it's less than 0, so we draw it downwards. So when sketching it, just make sure you add the units for everything and the values, so power is going to be in watts. Here's volt ampere reactive, and the magnitude of S is just volt amperes. All right, so that was part 2. Part 3 is asking to calculate the power factor. Just do that here. So that's straightforward. Power factor is just equal to cosine of theta. So that's the cosine of 3.33, and that gives us 0.998. You might not get full marks if you just write that, because usually when we write power factor, we want to specify, is it leading or is it lagging? And the reason for that is cosine is an even function. So when you take cosine of 50 or cosine of minus 50, it gives you the same result. So in this case, we need to write leading. And again, that's because theta is negative. Okay, cool. Part 4 is an understanding question. So it's just asking, what is the ideal power factor value? Hopefully you all know what that is from labs. So that's unity power factor. And the reason that is ideal is essentially what this triangle will become is just one line without any reactive part. That means there's no reactive power, which would minimize the current draw in, say, a circuit or, for example, transmission lines, and that's effective in terms of cost, essentially. Reactive power is generally not very useful, so we try to minimize that by having unity power factor or close to unity. Okay, Part B is power factor correction. Yep. So we're given a new circuit now. So again, we have a voltage source, which is 240, the phase of 0 volts RMS, and we are given a load, and we're not told any information about the impedance of the load, but we only have information about the power. So we know it's got 1.2 kilovolt amperes, so that's the apparent power. And we have a power factor, which is 0.65 lagging. And the question is asking us to determine the type and value of the circuit element, which when connected in parallel with the load will raise the power factor to 0.95 lagging. So essentially we want to transform this to a 0.95 lagging. Right. I'll start by sketching the power triangle, and that's generally the best approach to do these questions. So I start with the old, and then I'll add the new. Essentially, want to connect something here in parallel. In this case, because we are going from something which is not very lagging to something which is more lagging, we need to add a capacitor, which is a leading element. So yeah, leading element will counteract the lagging effect. So we want to add the capacitor in parallel. I'm going to sketch the old power triangle and the new power triangle. So in the old power triangle, because this is lagging, we're going to have an upwards triangle. So this is theta 1, that's P, and this is Q. And we are given S is 1,200. Theta 1, we can calculate directly from the power factor. So that's the inverse cos of 0.65, which gives us 49.5 degrees. To calculate average power, that is just apparent power times the power factor. So that's just basic trig rules. And that gives us 780 watts. And we can calculate Q by doing S times sine theta. So Q is equal to S sine theta, and that gives us 911.9 volt amperes. So that's all the information we need given the initial circuit. We want to modify this to increase the power factor. What that means is reducing theta. So essentially, this means we're going to have smaller triangle like that with a new theta 2. Because we're adding the element or the capacitor in parallel, that essentially means power, average power you can assume to stay the same. So this P is the same as the original P. We're going to get a new Q dash now for the reactive power. And we're going to have a different apparent power as well, but we don't need to calculate it in order to solve the question. So we start by calculating theta 2. That's inverse cos of 0.95. And that gives us 18.2 degrees. We know P, so to calculate Q dash, we can do P times 10. We can do P tan theta, which gives us 256.5 volt ampere reactants. So now we essentially know how much reactive power we need to add into the circuit in order to modify the power factor. So we know we can calculate the difference in reactive power, which is Q minus Q dash. That difference of the reactive power is going to come from the capacitor. So the capacitor is the source of the additional reactive power. If we subtract them, get 655 volt ampere reactives. And now the question is, how do we relate reactive power to an actual value for the capacitor? So the way we do that is essentially by relating it to the formula, which is V squared divided by the reactance of the capacitor. This formula is analogous to P equals V squared on R. It's similar, except we're using reactive power instead of real power and reactive impedance instead of just resistance. In this case, XC is just equal to 1 over omega C. We're just taking the magnitude because complex numbers don't matter here. So this gives us delta Q is equal to VRMS squared times omega C. And so we can rearrange this to get C, which is equal to delta Q over VRMS squared times omega. Delta Q just calculated. VRMS is 240 volts, which is given in the question. And omega is 2 pi f, where f is 50 hertz, also given in the question. So we do that, calculate, and we get 36.2 microfarads. All right, that's all of question 1. Are there any questions on that? Yeah.
We had it like in the lesson, we needed to add an inductor.
Yep.
In parallel.
Yes. So in parallel with an inductor, it would be pretty much the same thing. The only difference is that now we're gonna have XL instead of XC, and XL is equal to omega L. But everything else stays the same. The other difference is that this triangle will be flipped. But in general, you won't have situations where you need to add an inductor in parallel because most loads are inductive. And so we correct by adding a capacitor. All right, let's move on to question 2. So question 2 is about transfer functions. We have circuits. And we are asked to calculate the transfer function hj omega, which is I over In. This one is very straightforward because it's just a simple current division. So the formula for current division, if we have here, so if we've got something like this, have Z1, Z2, then we have I2 is equal to I times the, so on the top we have the impedance that we're not interested in. So in this case, if we want to calculate I2, we put Z1 on the top, and then at the bottom is the sum of the two impedances. And then similarly for I1, you would put Z2 on the top. So in this case, we can just apply that directly. So I j omega. And the reason we work in the frequency domain here is because obviously you have an inductor, which is frequency dependent. So this becomes ij omega. So yeah, applying the current division gives us this times so the current that we're not the impedance we're not interested in is R1, and that's divided by R1 plus R2 plus j omega L. And that is our transfer function. So when we divide by I in, that's going to give us h j omega. So this would be our transfer function. All right, next part is asking us to find an expression for the magnitude, for the magnitude response of the transfer function, and then sketch it with a few points. So essentially, find the magnitude of hj omega. So when we have a fraction and we want to find the magnitude of that, that's essentially just the magnitude of the numerator divided by the magnitude of the denominator. So that's the magnitude of R1 divided by the magnitude of this, which is in this case the square root of the real part squared plus imaginary part squared. So that's just complex numbers. In this case, we get R1 squared, R1 plus R2 squared plus omega squared L squared. So what this is telling us is we have a transfer function which gives us the magnitude at any frequency that we want. And then it asks us to sketch the graph with a few points. So let's just calculate a few basic points. We start with 0. So if we have 0 over here for omega, then that's going to be R1 plus R2 all squared, square rooted. So that's just R1 plus R2 at the bottom. So we'll have R1 divided by R1 plus R2. And the question gives us the values of the components, and it tells us R1 is equal to R2. So in this case, that's just going to equal half. And then you can try with any other random points since the question doesn't really specify what it wants. But what you could do here in this case is look at what can we substitute into omega to give us something which simplifies nicely so that we don't have to plug in lots of numbers and possibly do calculation errors. So in this case, if we use omega equals to R1 plus R2 divided by L, what that means is this will be R1 plus R2 squared divided by L squared. So the L's are going to cancel. And then we're just going to combine the R1 plus R2 squared. So that would give us, to do the algebra, give us R1 divided by 2 times 2 R1 squared, noting that R1 is equal to R2. And so you can see the R1s are going to cancel, and that gives us 1 over 2 root 2. So that's smaller than the value at 0, which is a half. So that means our magnitude response is going to be going down. Finally, for the last point, we could do as omega tends to infinity. So as this gets very large, the denominator is going to tend to infinity, which means our magnitude response is going to tend to 0. Yes.
That's the reason why it's
We're just trying to cancel out the L. Yeah, so there's no imaginary point. Yeah, there's no specific reason why I chose this. Like you could do with any random number. It's just to get a nice simplified form. This one, yeah. And so when we sketch that, that's gonna look something like this. So here that's our omega, and that's magnitude response. At 0, we have half, and at this value, which is R1 over R1 plus R2, we have 1 on 2 root 2, and then this goes to 0. Let's move on to part C. So this is saying suppose two experiments are conducted on the circuit. So the first applies a current which is like this for a specific value of omega 1, which is 100 meters per second. And we also have another function, which is sine omega 2t, and that is 10 kilorads per second. So it asks us to determine the amplitudes of the output currents for each experiment. So the way to go about this is just by using the transfer function. So we know that our output current is the magnitude of the output current is the magnitude of the transfer function times the magnitude of I in. Yeah. Yes. Is it R1 over R1 plus R2? R1 plus sorry, yes, R2 yes. My bad. Thank you. Yeah. Thanks for that. So in this case, the value of the magnitude of I in, because it's just a sinusoid, and it only occurs at one frequency, that means its magnitude is just whatever coefficient we have here. So in this case, it's just 1, regardless of the frequency. Another way to think about this is in the frequency domain, the magnitude of sine is just one line at a specific frequency. So at omega 1, for example, and that magnitude is the coefficient of the sine. So because we're multiplying our transfer function with just one line at one frequency, what that means, it essentially samples the transfer function at that frequency. So this is going to be equal to the magnitude of h at omega 1. So for example, this could be I1, the magnitude for I1, which is for this input current, and similarly I2 will be transfer function evaluated at omega 2. So essentially all we're doing is plugging in those values into this formula here. And evaluating that gives us 0.4975 amps for this one, and 0.04975 amps. A quick sanity check, we can see that it's roughly 10 times smaller when we increase the frequency, and that is consistent with the graph. So as we go further to the right, we can see the value decrease. Part 2 is asking to compare the two results and explain why one amplitude is greater than the other. That's essentially because of the nature of the magnitude response we have. So in this case, we've got a circuit which is inductor with a resistor, and that creates a low pass filter. So this is a low pass filter, which only allows low frequencies to pass through and attenuates the higher frequencies. So yeah, that's essentially the reason. Higher frequency is going to get attenuated, so that's why it's much smaller. All right, last part of the question is Fourier transform. So now we are given an input current which consists of lots of harmonics. So we have sine pi t minus 2 on 3 pi cos 2 pi t plus some other stuff which I'm not going to bother writing because it's not relevant to the question. So sometimes the question might give you some information that you don't require to confuse you, but you actually don't need it. So it's asking to determine the value of the DC component of the output. So because it's just asking for the DC component of the output, we don't need all the higher harmonics. So in this case, we want to calculate I. So we know that I in at omega equals 0, which is the DC component, is just the DC value here, which is 1 over pi. And so if we want to calculate I out, the DC component of I out, again, that's just using the transfer function. So that's going to be the magnitude of H at 0 times the magnitude of I in at 0, which is 1 over pi. And H0 we've already evaluated previously, that's equal to a half. So that gives us 1 over 2 pi amps. Okay. Next is asking to explain why this value of the DC component is expected when we have R1 equals R2, considering the impedances of the circuit. Let's take a look at the circuit. Essentially, because this is at DC and the frequency is 0, that means the inductor acts as a short circuit. So you can think of this inductor as a short circuit when the frequency is 0. In that case, you just have a simple current divider, which is R1 and R2, which means the output current through R2 is going to be half of the input current. So that's how we go about it. So the input current is 1 over pi. Doing a current division for two equal resistors will give us 1 over 2 pi. All right, that's question 2. I kind of skimmed over it quickly. Are there any questions about it? Okay, cool. Let's move on to question 3. So this is giving us a graph and asking us to find the Fourier series. I'll just sketch the graph first. And then this. And we are given this is A, which is equal to 2. And this here is T, which is equal to 8. And we're required to calculate the trigonometric Fourier series up to the 5th harmonic. So Fourier series, essentially what that is, it's essentially just an infinite sinusoidal representation of a periodic function, and it's expressed as follows. So we've got a DC component plus an infinite sum of cosine terms, which have frequencies at multiples of the fundamental frequencies, integer multiples of the fundamental frequency, plus an infinite sum of sines. And the way we calculate the ANs and the BNs is just through an integral formula. So AN is equal to T over 2 over T, the integral from 0 to T of f of T cos n omega 0 T dt, where f of T is just the function that we want to express as a Fourier series. Similarly, Bn now we could brute force this and calculate AN and BN directly, which is going to be 2 integrals. But there's a clever observation that we can make here about the graph, particularly that's an odd function. So in this case, we have ft is equal to, or f of minus t is equal to minus f of t. Essentially what that means is the left-hand side of the graph is a flipped version of the right-hand side. What that allows us to do is know that an and a0 is 0. So in that case, we don't actually have to compute the integral. So because it's an odd function, they're going to equal 0. Similarly, if we have an even function, which means the left and right side of the y-axis are mirrored, we can directly deduce that Bn is 0. Some functions may not be odd or even, in which case you'll have to calculate both An and Bn. But in general, there might be some tricks that you can do in an exam question. Now, another simplification that this odd function allows us to do is transform this integral here to just half a period and have this as 4 over t. Generally, that might be easier to compute because we just have to worry about half a period instead of the whole period. So in this case, if we were to do the whole period, we'd have to do it up till t equals 8, which means we have 2 sections to integrate. Whereas half a period will be around here, so we only have 1 section. Oops, we'll only have 1 section to integrate. So both formulas apply, but one might be a lot easier than the other. So now we know that Bn is equal to 4 over t, the integral from 0 to t over 2 of f of t. F of t in this case is just equal to a from time equals 0 to time equals 2, and time equals 2 to time equals 4 we actually don't need to worry about because it's just 0, so we don't need to integrate anything. So that is a times sine n minus 0 t dt. From here on, it's just simple computations. So I'll take a out, and integrating sine is going to give us 1 over n omega 0, because we're dividing by the argument here. And that's going to integrate to a negative cos and omega 0 t, and that's going from t over 2 to 0. And now we can note that omega 0 is just 2 pi over t. So we're multiplying t by 2 pi over t, so the t's are going to cancel. And we're going to get 4a over 2 pi n. Here. And then we substitute t over 2 and 0 into the cosine. So that's going to give us minus cos n omega 0 t on 2. And cosine of 0 is just 1. So that's going to be minus 1, which gives us plus 1. It's very easy to make sign errors with the negatives in Fourier series questions. So just make sure to write everything out and watch out for like double negatives and everything. Again, here, this is just 2 pi on t. So the t's are going to cancel, and the 2's are going to cancel as well. Did I do something wrong? That's fine. Okay, and then if we evaluate that, so we're going to have 2 pi divided by 2. That gives us a pi. And then the t's are going to cancel out. So that gives us 4a over 2 pi n cos that's n pi plus 1. I think there should be a half here. I think I might have missed it somewhere.
The two from 2 pi cancel the over 2.
Yep, that's right. So yeah, I'm trying to see. Oh, I'm just forgetting. Wait. Okay, I see. I did a silly mistake here. So, this t here, is a different t, from this t. I should have simplified that earlier. That's because we said we're actually just integrating from 0 to 2, not the whole time period, which t is equal to 8. So that's why. So I should have just set that equal to 2, and then we substitute 2 over here. That's going to be n omega 0 2, and omega 0 is 2 pi on t. Now this t is actually 8, so that gives us 4 pi over 8, which is 0.5 n pi. Now we can substitute the a is equal to 2. So that gives us 8 over 2 pi n, which gives us 4 over pi n, and that's 1 minus cos 0.5 n pi. So remember what this is. This is just Bn. And now we can compute that for the first 5 harmonics, which is what it wants. So B1, here's just substitution. There's nothing special. B1 is 4 over pi. B2 is also 4 over pi. B3 is equal to B3 is equal to 4 over 3 pi. B4 is equal to 0. That's because when we have n equals 4, we're going to get cos 2 pi, so we get 0. And B5 is equal to 4 over 5 pi. Now we just rewrite that in terms of the summation form. So that means our current is equal to sum from 1 to infinity of Bn sine n pi t on 4. So that n pi t on 4 is coming from the fact that n omega 0 t is particularly n omega 0 is just 2 pi on t, which is 2 pi on 8, which is pi on 4. And then we just rewrite it as the first 5 harmonics. So that's just the b's as the coefficients of sines and different frequencies. So 4 over pi sine pi on 4t plus 4 on pi sine pi t on 2, and so on. You can just substitute for the other 3 sinusoids. Right, part B is asking us to sketch the amplitude spectrum. This is similar to the magnitude response that we sketched in the previous question. It's just now because it's discrete, it'll be just lines instead of a continuous function. So on the x-axis, you could put either n or omega. It doesn't really matter, they're equivalent. In this case, I'll just put n for convenience, and we have 1, 2, 3, 4, and 5. And over here, we are just sketching the magnitude A. I'll note that the magnitude A is a function of both AN and BN. So in particular, if we had a signal where AN was not 0, this would mean A is equal to the square root of AN squared plus BN squared. That's going to be a function of n. So in this case, because AN is 0, this is just going to be equal to BN. So Bn, we just use these values, we calculate it and sketch them on the graph. So we're going to have 4 over pi, 4 over pi, 4 over 3 pi. This one is 0, and that's 4 over 5 pi. Next part. So now we're given a circuit. We have the same source, and we have 10 ohm resistor. We have a voltage across that resistor and 2 farad capacitor. And we're asked to calculate that voltage up to the 3rd harmonic. So we just start with simple circuit analysis. We can do current division here. Or actually, I'm just going to simplify this circuit to one load. And so the voltage here is just going to be the current times the equivalent impedance. So in this case, voltage as a function of omega, we're working in the frequency domain, is the current times the parallel combination of the resistor and the capacitor, which gives us R times 1 on j omega c over R plus 1 on j omega c, and that simplifies to R over 1 plus j omega RC. Now we can just simply substitute the different harmonics into this expression. So we can substitute omega 0, omega 1, and omega 2, where omega 1 is just 1 times omega 0, and omega 2 is just 2 times omega 0. So V omega 0 is equal to the magnitude of I at omega 0 times R over 1 plus J 0. So that's just R times sorry, we're substituting omega 0, not 0. So omega 0 is the 2 pi over t from the previous question. And this shouldn't say magnitude. So we're interested in both the magnitude and phase here. So this is just going to be a complex number with both a magnitude and a phase. And then this is times RC. So we just plug that into the calculator and we'll get this is equal to 0.81 with a phase of negative 86.4 degrees volts. And then we just do the same for the second and third harmonics. Now the question, so remember our current was expressed in terms of sign. So essentially what that means is that this phasor is in terms of sign. So when we convert back into the time domain, that's going to be a sine instead of a cosine. So we go back to the time domain, and that's going to give us 0.81 sine omega 0 t minus 86.4 degrees. And we can do the same for the omega 1 and omega 2, and that will give us 0.45 sine omega 1 t minus 88.18 plus 0.09 sine omega 0 t minus 88.78 degrees. So all we're changing here is the n that is being multiplied at the omega 0. So over here, we're just adding 2 or times 3. So yeah, just the same calculation on your calculator. Any questions about question 3? Yes.
Did you convert from the sign to the sign?
Yes. So the reason for that is because this has a phase of 0. And that phase of 0 is referring to a sine phase. That's based on how we defined this current. Yeah. Any other questions? All right, cool. Let's move on to question 4. So here, this is a resonance question. We're given simple RLC circuit. And we're asked to find the resonant frequency, the half-power frequencies and bandwidth, and the quality factor. This will be quite similar and just following from the slides. Definition of resonance is essentially when your imaginary components in the circuit cancel out. So in this case, in resonance, this is essentially as if it's like this. It's just a resistor because your inductor and capacitor, their impedances cancel out at a specific frequency. So we want to work out what that frequency is. So the way we do that is first by calculating the impedance of the inductor and capacitor and solving for omega to see how they cancel out. So our equivalent impedance is R plus J omega L plus 1 on J omega C. So then the imaginary part of the impedance is omega L minus 1 over omega C. And we set that equal to 0 and then solve for omega 0, which is the resonant frequency. So solving for that gives us 1 over root LC. And then you can just substitute in the values of L and C and get a numerical answer. Right, next to calculate the half-power frequencies and bandwidth. I'll just sketch what this would look like. So we have an understanding. So we have frequency here, and let's say we have the magnitude of some transfer function here, could be voltage over voltage. For an RLC resonant circuit, this gives us a bandpass-like shape, where resonant frequency is where the peak occurs, and half-power frequencies are essentially when we have half power, which is equivalent to having 1 over root for the voltage. So if this is, that's A, then at the half power frequencies, we have A over root 2. And then the bandwidth, so we can call the half power frequencies as omega H and omega L. And then the bandwidth is just the difference. And we also define something called quality factor, which is the resonant frequency divided by the bandwidth. So quality factor tells us about the selectivity of the filter. Essentially what that means is if we have a high quality factor, it's going to be quite narrow and have a high peak with a low bandwidth, whereas a low quality factor will be broader. So to calculate the half power frequencies, for a series circuit, that occurs when the current here is 1 on root 2 of the maximum current. So we want the magnitude of I to be I max on root 2. The maximum current that occurs at resonance. So essentially when we have this circuit over here. So the maximum current is just the voltage divided by the resistance. So that is equal to the magnitude of V divided by R divided by root 2. And that gives us 0.1 over root 2. So we want the magnitude of this current to be equal to 0.1 over root 2. Now we just find an expression for that current. In this case, it's just a simple voltage divided by impedance. So I is V over Z equivalent, which is R plus J omega L plus 1 on J omega C. Now that's just I as a complex number or as a phasor. We want just the magnitude. By taking the magnitude, we have magnitude of V divided by square root of R squared plus omega L minus 1 over omega C whole squared. And we want to set that equal to 0.1 over root 2. You can already tell this is going to involve quite a bit of algebra. So I'm just going to multiply both sides, cross multiply. So here we'll have root 2 times the magnitude of V divided by 0.1. And then I'm going to square this as well, same time. So that squared is equal to R squared plus omega L minus 1 over omega C squared. Now you might be tempted to just expand this and end up with like a quartic, but that's going to be like a lot of algebra. So a smart trick you can do here is realize that you can just solve for this as a variable. And then once we have this as a variable, we can solve it again to find what omega is. So essentially, I solve omega L minus 1 over omega C is equal to this expression minus R squared all square rooted. So that's a lot faster than solving it by expanding and doing a lot of algebra. Now this is going to give us two values because we're taking the square root. So this is going to be plus and minus. And you do the substitutions and you get plus or minus 200. Now omega L minus 1 on omega C is equal to plus or minus 200. Now we can solve this as a quadratic to get the values of omega H and omega L. So I'll just multiply everything by omega C and move that to the other side. And I'll normalize this term. So we have omega squared plus or minus 200 over L omega minus 1 on LC. That's equal to 0. Now this is essentially as if it's two quadratics because we have the plus and minus here. Mathematically, I know that if I choose the minus, then I'm going to have a quadratic with two positive roots. So I can just discard the plus straight away and know that the negative is going to give me two positive roots, which is our high and low frequencies. And those are positive. If you don't know that, you could solve both quadratics and just discard all the negative values. So in this case, I'm just going to ignore this and solve the quadratic with two negative signs. And we do that. It's going to give us, oh no. Seems like the pen died. So let's take a break and then let's continue this after it's charged. Yeah, so we substitute the values in and we get omega squared minus 20,000 omega minus 10 to the 10 is equal to 0. You put that into the calculator or use the quadratic formula and we get two values. And omega h is, I think, and that's radians per second. From that, we can simply calculate bandwidth as omega h minus omega L, which gives us, I think that would give us 20K. Yeah. And then we just calculate Q by doing omega 0 over bandwidth. So that is our omega 0 was 1 on root LC, which is equal to that gives us a really large value. Over the bandwidth. Is equal to 5. So the question does give a note that the quality factor is less than 10. Essentially what that means is omega omega L and omega H might not necessarily be symmetrical around the middle. Whereas if the quality factor was much higher, you can approximate that it's symmetrical. And so you can use the formula directly for quality factor with an RLC circuit. Well, because Q is not greater than 10, we have to sort of use this method and do it manually. Sorry? The quality factor? That's 20,000. So we have 1, 2, 3, 4. Yeah, so 100 divided by 2 is 50. You are right. But it should be 5. So I think I added an extra 0 at the top. So, yeah. All right. There are any questions on that? I'll move on to magnetically coupled circuit question. Now, these are generally like free marks in your exam, and there most likely will be magnetically coupled question. The main thing to look out for is just watch out for the sign convention and make sure you have the current directions right. In here, we're asked to calculate V out. So we can just do mesh analysis, which is pretty much the only way you can solve these type of questions. I'll start by simplifying these two components here. And I'll actually label everything with variables as well. So that's R1, that's L1, that's L2, that is C, and that is R2. You might have noticed I've already just been using variables and doing minimal substitutions for every question. I recommend doing that in the exam as much as you can, just to avoid numerical errors with calculators and save time. You don't want to be using the calculator a lot while solving the question. So combining the capacitor and the resistor in parallel, that's R2 in parallel with 1 on J omega C, which gives us R2 over 1 plus J omega R2C. That's equal to 0.5 minus J. Now I'll label the currents I1 and I2. I'll just redraw what this became. So this is now the inductor with Z equivalent. And V out is just the voltage across that parallel load. And now we'll write the first mesh equation in this mesh. So we have I1 times R1 is the voltage drop across the resistor. And we have the voltage drop across the inductor due to the self-inductance is J omega L1 I1. Now we're going to have another voltage drop at this inductor due to the current that's going here into this inductor. So essentially, the current that enters this dot is going to induce a voltage with positive polarity at the dot of the other inductor. So in this case, I have the current entering the dot based on my label. That's going to give a polarity. What happens? So that's going to give a polarity which is positive at the dot of the inductor in the mesh. And we have the current in the mesh is also entering the dot. So there's no conflict in terms of polarity between the current and the induced polarity from the other inductor. So in this case, it's going to be a plus. And that's going to be J omega. We use the mutual inductance, M. And the current is going to be the current that induced the voltage, in this case, I2. And that is equal to the source voltage, which is 12. Similar thing for the second mesh. So we're going to have I2 go through Z equivalent, and then we'll have self-induced voltage from I2, and we'll have a mutual induced voltage from I1. We have Z equivalent I2 plus J omega L2 I2. And similarly, we'll have the same term for the mutual inductance, except I1 instead of I2. In general, these two signs should always match. Like, you won't have a case where you have a plus and a minus, as long as you've been consistent with the way you've labeled the currents. So in this case, I've labeled both currents going in the same direction. So you'll be consistent. You'll get either two pluses or two minuses. If you've done something weird with the currents and labeled this like that and this like that, that might not be the case. But in general, it should always be consistent. And we can check based on the direction of current. So here, the current is entering the positive dot. That induces a voltage, which is positive here. And that current is entering through the positive terminal. That's why we have a plus. If we had a conflict, for example, the current entering the negative terminal, that's when we would have a minus. And that is equal to 0. Now, solving simultaneous equations with complex numbers can be annoying, and it is error prone. So hopefully you guys heard about this before. It's called Cramer's rule. It just makes solving simultaneous equations very easy. So I'll first simplify these two equations. So the first equation gives us 2 plus J16 I1 plus J4 I2 equals 12. And the second equation gives us J4 I1 plus 0.5 plus J7.5 I2 is equal to 0. What Kramer's rule tells us is we just calculate the determinant of these four numbers. So we call that D, which is the determinant of the coefficients of your I1s and I2s. And then let's say we want to calculate the value of I2. That's just dividing a determinant D2 by D, where D2 is similar to this D, except we substitute the column or the variable we're interested in with the values on the right-hand side. So that means is, in this case, I2 is on the right. So we substitute these two values with 12 and 0. So D2 is the same determinant, except I'm going to substitute the right column with 12 and 0. Similarly, if you wanted for I1, you would substitute 12 and 0 into the first column instead. So calculating these two determinants is straightforward. So this one's just 2 plus J16 times 0.5 plus J7.5 minus J squared, which is a plus. 4 times 4 is 16. And this one, we have this number times 0, so we get a 0, and then minus J48. And so if we divide these two values, we get I2 equals 455 with an angle of 102.6 degrees. So that's generally a lot easier than trying to do substitutions and doing a silly error somewhere with a sign. Now we're almost there. The question is asking to find V out, not the current. So in this case, V out is simply just I2 times Z equivalent. So essentially, the voltage drop here is the current times Z equivalent. And because we've labeled the current entering the positive terminal, then it's just positive. And we do that calculation, we get 0.32, 57.6 degrees, which in the time domain is 0.32 cos 4t plus 57.6 degrees. So here we're using cos because the source was given as cos. Right, any questions about that? Okay. The question is also asking to calculate the coupling coefficient. That's just applying the formula. K is equal to M over root L1, L2, which is 1 over root 8. Coupling coefficient essentially just tells you how strongly coupled the two inductors are. So that ranges between 0 and 1, 1 being the highest, which would be a transformer, and 0 being essentially not coupled. All right, last question is Fourier transform. this. So we are given this function and asked to calculate the Fourier transform. So minus 1, 1, minus 1, 1. So the Fourier transform is similar to Fourier series. The only difference is that instead of doing it for a periodic function, we want to find the frequency domain representation of any function. So that doesn't have to be periodic, like in this case. Fourier series only gives you a discrete set of frequencies, whereas Fourier transform gives you a continuous set of frequencies. So the function f of t in the frequency domain will be capital F of omega, where omega is continuous instead of discrete as in Fourier series. To find the Fourier transform, which has notation like this, we just apply an integral that goes over all time of the function times e to the minus j omega t dt. So essentially, we just compute that integral. In this case, the function is 0 everywhere except here. So we have two sections to integrate. So we've got that one and this. So we're going to split that integral into two. That's going to be 1 times e to the minus j omega t dt, going from minus 1 to 0. And the other integral is minus 1 e to the minus j omega t dt, going from 0 to 1. So this is just simple integration. I'm going to have 1 over minus j omega times, it's just an exponential, so it integrates to the same thing, from 0 to minus 1. And similarly, we're going to have minus 1 on minus j omega, e to the minus j omega t, from 1 to 0. I'm going to factorize the 1 on minus j omega. And now that gives us, just substitute. So j omega 0 minus e to the minus j omega minus 1. And then minus e to the minus j omega 1 minus e to the minus j omega 0. Here we've got e to the 0 and another e to the 0. This is a plus, so we have e to the 0 is 1, so 1 plus 1 gives us 2. 1 on minus j omega. We have a 2, and then we have the other terms, so minus e to the j omega minus e to the minus j omega. Now you could leave it in this form as your final answer, but you could simplify it a bit more by noticing that this is similar to the cosine function. So we know that cos omega is equal to a half of e to the j omega plus e to the minus j omega. And similar thing for sine. So we have sine of omega is 1 on 2j e to the j omega minus e to the minus j omega. So applying that, you could get 1 on charge for a bit. So substituting the cosine here, we get 1 on minus j omega, 2 minus 2 cosine omega. And just one additional step gives us and we can write our answer like that. And the final question of this paper is asking us to find the Fourier transform of 1. Or particularly, we want to show that the Fourier transform of that results in 2 pi direct delta. So just a reminder about the direct delta function. This is just a vertical line at omega equals 0 with an amplitude of 1. And so we can shift that around by modifying the argument. So for example, delta omega minus 2 would be over here at omega equals 2. Essentially, it's a mathematical way of representing a single frequency, which occurs from sine and cosine. So now you might be tempted to just apply the definition of the Fourier transform directly on f of t equals 1. But if you evaluate this and do the integral, you'll run into an issue. And that issue occurs because the integral essentially diverges. So it's not convergent, and you won't be able to evaluate it. So in order to show this, we'll need to use a property. A way to sort of be able to identify that is the question says use a method of your choice. That usually implies you'll need to use a property because you might run into issues if you directly evaluate it. And there's 2 ways to go about this. I think the easier way to think about it is just by considering the graph in the time domain. So we have f of t is just equal to 1. And we cannot evaluate that. So instead, we can evaluate something which we know its Fourier transform. So in this case, we can create one using two unit step functions. So we could have a unit step function, which is ut, and then another unit step function is equal to u of minus t. And so if we add them together, we end up getting 1. So 1 is equal to ut plus u minus t. And so the Fourier transform of 1 is just the Fourier transform of ut plus the Fourier transform of u minus t. And to evaluate the Fourier transform of ut, that's straightforward because we can just use a property, or not a property, it's just directly given in the Fourier transform pairs table. So you can apply it directly. So we are given in the table that ut has a pair pi Dirac delta plus 1 on j omega. So that's the Fourier transform of ut. We'll also need to figure out the Fourier transform of u minus t. Now, to do that, we'll need to apply a property called scaling. Or we don't even need to use a scaling property. We can just use the reversal property, which states that if you have f of minus t, that has a Fourier transform f minus omega. So essentially, we replace all the omega with minus omega. So that's equal to Dirac delta minus omega minus 1 on j omega. So this means that the Fourier transform of 1 is I Dirac delta 1 on j omega minus 1 on j omega. So we can see that these cancel. And then what we can do about this one is we note that flipping a Dirac delta essentially doesn't have any effect on it because it's an even function. So yeah, this is just centered at 0. So Dirac delta of omega is the same as Dirac delta of negative omega. Yeah. So we end up with 2 pi Dirac delta omega as required. All right, any questions about Fourier transforms? All right, that's the end of the 24 paper. I'm happy to take any other questions about specific questions from any past paper that you want. Just tell me the year and the question, and I can go through it. No worries. It's over there. All good, thank you.
Thanks a lot. Have a great tutorial.
Yes.
I'm sort of RAM question.
feel like this one, there is a resonance question.
Yeah.
You derived like this for the.
Yeah.
Resonance
There's some
frequency.
steps.
Yeah.
Um,
I understand how you did that.
Okay,
But,
yeah.
I seen some other similar questions.
Yeah.
It was like parallel.
Hmm.
Can you just use this formula or is
No.
it different?
It will be the same formula, so
Alright.
it's RLC parallel with the current source,
Mhm.
but the way you derive it will be using admittance instead of impedance. If you use impedance, you'll get a y by 0. Yeah, okay.
Right. But so
But it will be
does
the
this work
same. Yes.
for any RLC circuit?
Yeah,
or-
either
oh,
parallel or series will be the same. Yeah.
okay.
General question
Yeah.
of like how the midterm is structured. So
Yes.
there's gonna be like AC, like RLC or series or parallel, like AC resonance,
Yeah.
and then of course power triangle or power question. That's one. And then Fourier series. I was about to ask for Fourier series about the even case.
Yeah.
Because the average or 1/t.
Yeah.
Does that multiply by 2 and it's over half a period from 0 to half a period?
That's when it's either odd or even.
Yes,
Yeah.
in the even case.
Yeah. So in the even case, it's over half a period as well. Yeah.
And it's multiplied by 2, so
4 over
2 over t.
Yeah. No, so the original one is 2 over t.
E-
And then
yeah,
when you simplify it to with odd or even, you go over half a period and then it becomes 4 over t instead of 2 over t. So
yeah, right. Uh,
so what was it?
Thank you.
Thank you. Yeah, so this one simplifies to 4 over t and
Yes.
half the period
yeah.
instead of this form.
Like or like in the even case where it's
Same
like,
thing as well.
so like this well, because in the odd case it's 0.
Yeah.
But for this it'd be 2 over t. No, that's like my main question. Of course, like of course an for the even case is 4 over t.
Yep.
But for that like the DC value, like the average, is that 2 over t?
Oh, for a0?
Yeah.
Oh, okay. Okay.
Sorry.
A naught. I think so. Then let's just check does I get it here? No.
No, it's a naught is, oh, they don't show you actually.
Yeah.
But like that's like just like average, right?
Yeah.
And it's 1 over t, and I was thinking, is it because you multiply it by 2, right?
No, in the case it doesn't change. Oh, actually, yeah, it might. I think it becomes t over 2 in the case when it's odd.
Yes.
But either way, both still hold. So even if you do the simplification, you can still use this.
Oh, I can still use like the over
And
0
even
t.
these ones, yeah. You can
Oh, okay, yeah.
It's just an alternative which makes it easier.
Okay, yeah.
Yeah.
And then magnetically coupled. That's most definitely gonna be on there, right?
Yes.
Yes.
Yes, it's the same format always usually. So you've got
Yeah.
magnetically coupled. You've got resonance. You've got something about Fourier series for transform. Definitely something about power.
I'm not too good at Fourier transform, and to be honest, like I was thinking maybe
it's the most recent topic.
Yeah.
But essentially it's just applying the integration.
Yeah, but I'm really terrible at integration. I'm like it's kind of a stretch for me to think of Fourier series. Like the fact that I was able to understand odd and even was like a miracle at this point. But yeah.
How do I? End.
And it will start.
It's